Okay, so first of all, thank you to the organizers for inviting me to be here. It's been a very interesting couple of days hearing all these different perspectives. And today I want to talk about galaxies in the context and how important spectroscopy has been for our field. We've heard a lot about the imaging, of course, in the last few talks, but I'll fully focus on a couple results from the past year or two. So before doing that, I just want to zoom out a little bit and show you a slide that I often show in my outreach talks, actually. And this is showing a simulation of a Milky Way-like galaxy. So what you see is at redshift 0, we have a very nice Milky Way-like system. And as you go back in time, you see that things become more messy. So it's this middle image is redshift sort of 1 to 2, so it's a look back time, also 8 gigayears, where things start to look like Milky Ways. But this very early epoch, where things are really, really messy, is something we really don't understand. So this later times we've been able to study using ground-based telescopes and Hubble, but this very early phase is really where JWST is so powerful. So what are the big questions that I'm interested in and that the field is interested in? It's actually very simply, it's just how do we grow a galaxy? But to be more specific, what we're interested in finding out is really when do galaxies build up their stellar mass? When do we start to form galaxies that look like our own Milky Way, and how does that happen? And also just how does galaxy growth differ at early times versus from that at later times? So even from the first images, so ERO images, ERS images, sparked a huge frenzy in the extragalactic community, where all these galaxies were discovered in an image that was, I mean, it was relatively speaking very deep, but for JWST, it's actually relatively shallow. And it already revealed these thousands of systems. And what people started to look into is really two main lines of research. I mean, of course, there are many projects, but I'll focus on two main areas to figure out how galaxies actually assemble and grow. So the first sort of item is to search for early Milky Ways, and that is a very broad definition, but basically things that look disky or could become disky. And I don't want to steal Jehan's thunder entirely, but this is a very nice comparison, I think, between what we saw with Hubble and what we see with JWST. And Stacy already showed this image as well. What is really nice is you see here 4 galaxies in lots of different filters, so different wavelengths. And what is important is that JWST shows a different image even at the same wavelength as Hubble. So Hubble showed all these sort of clumpy and messy systems at redshift 2, so that is a look-back time of about 10 billion years. But if we look in JWST, we see all these very smooth systems that look disky. So this is really interesting because this didn't really match our understanding really of what these early galaxies look like. Now, it's one thing to say that something looks disky, though, and it's another to actually confirm that you have a rotating disk. And that's especially true for these systems that are edge-on, so these sort of cigar-like shapes. So you see one that's I don't have a laser pointer, I think. It's the third from the top. Where it's hard to tell whether this is an edge-on disk or whether it's just an intrinsically elongated system, so like a cigar-like shape. And the only way to find out is to look at the kinematics of these galaxies. And this is something that people have been doing from the ground for many years. So this sort of shows you the landscape pre-JWST. So this is redshift 1 to 2. So nowadays we call that low redshift. And what you see here are little disks that we got, or other teams got using IFU data from the ground. And these color gradients show you the velocity gradients in these systems. So all these systems are, or most of these systems are rotating. Now at JWST, we go back further in time, right? So we want to figure out, do we also see this at higher redshifts? And are all these galaxies that we thought were clumpy actually also clumpy, or are they these smoother things? So there was this very nice paper from Erica Nelson using the NIRCam GRISM. So that was, if you're used to looking at GRISM data, the NIRCam GRISM has been amazing compared to Hubble. So there is this object, you see on the left here the image, So it's kind of this smooth system, and you see it as it is edge on. And if we disperse it in one direction, then you get this image in the middle. And so here the x-axis is velocity axis, and the y-axis is spatial axis. So it means that we're seeing this rotation curve in the galaxy at a redshift of 5. So this redshift has been entirely inaccessible from the ground. So it's a really nice demonstration of what JWST can do and how well we can actually resolve these massive systems with new instruments. But this is still a very massive galaxy. If we want to figure out how the Milky Way came to be, then we want to look at really the low mass galaxies that we think grow into Milky Ways at later time. So this is research that I've been working on quite a lot. So here you see one object where on the right you see the image, and then we disperse it in one direction. So you get, again, one velocity axis and one spatial axis. And if you squint, it's kind of small, you can see that there is this gradient in this system. And we don't just see this in one object, we see it in multiple objects. This was just from very first data as part of the JADES survey, so that's the NERCAM and NERSPEC GTO. And what is remarkable about these systems is not just their high redshift, but also that it's really probing an entirely new regime. So in blue, you kind of see everything that was done from the ground before in stellar mass, star formation rate, and size parameter space. And what you see is these objects really lie outside of these, well, outside of the parameter space that we've been probing so far. So it's really exciting. If it, okay, there we go. So I spent a lot of time trying to model these systems, which is actually very tricky because NERSPEC is an amazing instrument, but it's a very complex instrument as well. So to actually extract the kinematic information from these data is very tough. But we're able to do it. And this is kind of a key result from the paper that we wrote. So the y-axis is kind of the level of rotational support. And what you can focus on is these gray points are from ground-based studies. And you can see that towards higher redshifts, so earlier times, the level of rotational support decreases. So you would expect this trend to sort of go down. But what we see with JWSTs, as these orange hexagons, is that they're kind of all over the place. So there are some objects that have very little rotational support, so they're very turbulent systems. But there are also a few systems that are possibly dynamically cold, so they might already have this rotation at a very early epoch. What is cool also about dynamics is that you don't just trace the kinematic structure, but you also get a sense of what the total mass of the system is, completely independent from any sort of spectral energy distribution modeling. And what is revealed was actually quite surprising, and that is if we look at the stellar mass and the gas mass we infer from this SED modeling versus the mass we get from the kinematics, which probes the total mass, then what we get from the baryons doesn't match the total mass that we infer from the kinematics. And this was a puzzle. It can mean a couple different things. So in the paper, we speculated on different ways we can resolve this sort of tension. But one of the options is that we're actually detecting dark matter in the centers of these very early galaxies. And very recently, this is a paper, actually, it's not, we're submitting it tomorrow, where we looked in the simulations to see what they predict for the masses of these very early systems. And we find, so these simulations are the small dots in the background, and the JWST measurements are these hexagons again. You see that they lie on top of the simulations extremely well, which is nice, maybe also a little bit boring, but it gives credence to this interpretation that maybe they're actually detecting dark matter in these early galaxies, so we're really tracing mass assembly in these systems, which is really exciting. Okay. So to switch gears a little bit, so kind of the second line of research that has been in huge focus and drawn a lot of attention. And that is to look for massive galaxies. And the reason why people are so interested in looking for massive galaxies is because you need only one really massive galaxy to break all your theoretical models. So that's why everyone is searching for these systems. And you might have seen the press on these objects published by Ivo Labbe, where he found in the ERS data these objects that are very young, so they're at the redshift of 7 to 9, so that's less than 1 billion years after the Big Bang. And they already have masses approximately equal to that of the Milky Way, right? So it's extremely massive. And that sparked all sorts of debates on archive and theoretical interpretations on how lambda CDM is broken, and so on. And what is the key about these systems is that there are these very compact red sources, and they have very strange SEDs. So in red, you see the SED here, and in green, you see the typical SED we inferred from HST. So what you see is that there's this very red very red slope in the optical, but it's kind of flat in the rest frame UV. So it's a very weird system. So it might imply a strong Balmer break or something else. So this is where the term little red dots kind of comes from. There's also Stacy already showed this. This is different work from Yola and Mate from the Fresco program. And he looked at some little red dots. So there are different systems from what I showed you on the previous slide. But he had spectroscopy for some of these from the NIRCam GRISM. And what all these systems have in common is that they all show in their Balmer line, so this is H alpha line, this two-component emission line. So there's a narrow component and a broad component. And how we interpret this is that this broad component comes from the material around an accreting black hole. And it has these very high velocities that gives this broadening. So this is now really a big debate. So do we really have the extremely massive galaxies in the early universe, or are all these systems just contaminants? Are they simply just dominated by these AGN? And then the second is, as Stacy also showed, is how do black holes and galaxies co-evolve? So we find that basically all these systems, if you try to estimate their black hole mass and their stellar mass, they lie above local scaling relations. So this is really a big puzzle that I think we're only now starting to dig into. And there are different teams, different programs looking into this, but I'll just plug my own program here. So this is, together with Gabe Bremer, we have a Cycle 2 program with NIRSpec, where we're targeting about 4,000 sources based on JWST NIRCam images from Cycle 1. And what we do is we really try to sample all the extremes in color magnitude space and with a very, very complete selection, just to try and figure out what these objects are. So in the images here, you see some of our targets that we actually observed in January. And actually, before I move on, I just want to highlight Gabe Bremer, who reduced, I think, all extragalactic publicly available data so far single-handedly, and also put it on an online archive, so that if you're at an institute where you don't have the computational resources to reduce so much data, you can still access all these great JWST images and also. So what is Ruby's doing so far? Well, we got our first data in January, and here are just a couple of these little red dots that we observed, and all of them have these broad emission lines. It's kind of hard to see, but the emission line furthest to the right is H alpha, and if you have a trained eye, then you can see that this is all broadened, and as for some of them, we also detect continuum, so we can actually do this very sophisticated modeling that Bingji Wang is actually leading to try and figure out, can we disentangle the galaxy component from the AGN component in these systems and work out what the relation between these two is there evolution? And there's one object in particular that we've been working on extensively and should be on archive very soon. So this is a very peculiar object. It's an extremely bright little red dot. And what is unique about this is that it has coverage from NIRSpec, NIRCam, and MIRI. So it's only the second source to actually have all this data, and I think it's the only source with this quality of data. So what you see here is the image stamps, so it's detected at 18 micron even. And then we have this very nice NIRSpec prism observation that shows all these emission lines and also a Balmer break. And we also have a slightly higher resolution spectrum. Maybe. Yes. So that slightly higher resolution spectrum is at the bottom, which resolves kind of the narrow and broad components of these lines. And what we found is, so we were planning to write a quick paper on it, but we very quickly realized that this object is extremely complex and none of our models work for this system. So in the end, Bingji developed this sort of strange composite model. I should say why it's so weird. So it's weird because it's very strongly attenuated, extremely red, but at the same time we have emission in the UV, which is not what you would expect when you have a lot of dust. And also in the mid-infrared, so these MIRI data points, I'm almost done, it's extremely flat. Whereas if you have a hot torus from an AGN, you would expect the mid-infrared to be strongly rising. This is very clearly an AGN, but with this very strange SED. It also has an absorption feature indicating an outflow. So it's a very complex system that I think we now sort of understand how to model this, but it's taken quite a while. And this is a sort of modeling that we're going to apply to our larger sample as well to figure out hopefully what this class of objects really. So with that, I'll leave you my summary. And really the summary is that spectroscopy of GWC is really cool, but we've only really scratched the surface of what is out there to discover. And there's a lot more